All right, this is topic 9.1, which is simple harmonic motion. We've already done simple harmonic motion in the standard level curriculum. This is the higher level material that's going to be additional to it. Essentially, the earlier material was mostly conceptual. This is going to get a little bit more mathematical in describing simple harmonic motion. So notice the essential idea. The solution for the harmonic oscillator can be framed around the variation of kinetic and potential energy in the system. We're going to really have to have a good understanding of the defining equation for simple harmonic motion, and then we're going to look at energy changes in simple harmonic motion. Look at solving problems, things like that. Notice that in this unit there are a lot of equations, so we'll tackle them and see what we can do here. Okay, so let's get started. First thing is just kind of a conceptual concept that there is a relationship between uniform circular motion and simple harmonic motion. If you imagine uniform circular motion, something moving in a circle of constant radius with a constant speed, if you look at the x or y position and or velocity of that object over time, you basically end up with simple harmonic motion. Now that doesn't make a whole lot of sense, but here's a visual of what we're talking about. So imagine this little red dot here is undergoing simple harmonic motion around, or circular motion around this circle. Let's review that for a second. So you know that if something is doing circular motion, at any instant, its velocity is tangent to the circle, and its acceleration is always centripetal towards the circle. Those two things are perpendicular to one another. And the force that's acting on it, the net force, is also acting towards the center of the circle. And that doesn't matter where we are in the circle. So there's acceleration, there's velocity. That's true for for uniform circular motion. Now, notice this gentleman right here, he's standing level with the table watching this object that's undergoing circular motion. So he's looking at it more in kind of one dimension rather than two dimensions. And what he would see is the object would appear to simply oscillate back and forth, back and forth, back and forth, just like simple harmonic motion. So from that, equations can be derived to explain simple harmonic motion by analyzing what's going on with circular motion. Fortunately for IB, we won't be required to derive those equations, but just kind of know that conceptually that's what's going on. So the first thing that we have to kind of tackle here is this concept of angular frequency, which is also sometimes called angular velocity. It will be represented by the Greek letter omega. Many of you are thinking, wait a minute, this is the Greek letter omega. And that is uppercase omega. This happens to be lowercase omega. So lowercase omega is what we'll use to represent angular frequency. And when we calculate it, it can be calculated with 2 pi f or 2 pi over t. In your data booklet, you will only actually find this equation. You won't find that equation, but since frequency is 1 over period and period is 1 over frequency, you can easily see how those two equations are related to each other. It's measured in radians per second, and I'll talk about here in just a second what angular frequency represents. But basically, it's the angle, something that's going through circular motion, it's the angle that it moves through per unit time. And we measure it in radians rather than degrees. And since there are 2 pi radians in a full circle, and since t, the time period, is the time it takes to complete a full circle, well, this is going to be the angle that something moves through and the time that it moves through a full circle. So that's how many radians it would move through every second. So that's basically the equation for angular frequency or angular velocity. I want to just show you a comparison between angular velocity versus linear velocity. So imagine we have a disk that's rotating in a counterclockwise direction here, and I'm going to look at two different points on this disk. Let's say point A right there and point B right there. Hopefully it makes sense that these 2 points will be going around in roughly a circle as best I can draw. And you can see that point B has a larger distance to travel for every revolution that it goes around. So you can imagine that the instantaneous velocity, or the linear velocity, how fast B is moving, has to be faster than A because it's going a farther distance in the same amount of time, since this is on a solid rigid disk. Another way of measuring how they move, or their speed, or their velocity, can be looked at rather than how far they're moving distance divided by time. let's look at the angle they move through over a given time period. And you can see that, point A and point B will move through the same angle in the same amount of time. In this case, we could say 90 degrees in a certain time period, or pi over 2 radians in a certain time period. And what we will call that is it's their angular velocity. So what we'll do is we'll figure out, okay, if they go around 2 pi radians, a full circle, 2 pi radians, and it takes the period to do that, then if we just take 2 pi divided by the period, that'll give us their angular velocity. Points A and B will have the same angular velocity, but they will have different linear velocities. Okay, we'll review simple harmonic motion again and the definition of it. If you want, hit pause and think about it for a minute and see if you can remember what are the properties that are required to create simple harmonic motion. I'll show you that here in just a second. So you get simple harmonic motion when an object has an acceleration that is proportional, directly proportional, okay, to its displacement. So if I double the displacement from equilibrium, I get double the acceleration. That's what it means to be proportional. But it's also in the opposite direction, okay? So we say is simple harmonic motion occurs when acceleration is proportional to displacement and in the opposite direction. And the equation that goes with that, this is the defining equation for simple harmonic motion right here. It's in your data booklet. A equals negative omega squared x. That's the acceleration of an object that's undergoing simple harmonic motion. And the reason this works is because you can see that the acceleration is directly proportional to displacement and in the opposite direction. That's what that negative sign means, okay? So this equation is basically what we use to define simple harmonic motion and define the acceleration of an object that's undergoing simple harmonic motion. Now, when we've talked about simple harmonic motion, there are two examples that we tend to talk about quite a bit. One of them is a mass on a spring, either hanging from a spring or on a horizontal surface that is frictionless and it's attached to a spring, or a pendulum. Those are the two most common examples of objects that are undergoing simple harmonic motion. In this topic 9.1, there are also equations associated with those two examples. So on a mass spring system, you will have the period equals 2 pi times the square root of m over k. It's hard for me to do that in the computer, so I just raised it to the 1/2 power, but recognize that that means this is all square root of m over k. That is in your data booklet. Notice that the period on a mass spring system, the period is affected by the mass that's attached to the spring and the spring constant k, which is unique to each spring, okay? However, that there is no effect on the period of the amplitude of oscillations. So larger oscillations and smaller oscillations should all have the same period. When we get into a pendulum, the equation, this is also in your data booklet, the period of a pendulum is 2 pi times L over G, where L is the length of the pendulum, G is the square root of L over G. L is the length, G is the gravitational field strength. Notice in this one that the mass hanging from the pendulum does not affect the period, and neither does the amplitude of oscillations or the angle of release. The only thing that affects the period of a pendulum is the length of the pendulum and the gravitational field strength. And again, just to reemphasize, in both of these cases, the period is not affected by the amplitude of oscillations. Small, large, the period should be the same for all oscillations. All right, let's give it a little practice here. So hit pause, work through this one. If you want to time yourself, give yourself 90 seconds, which is the time you'll have on the IB exam, and see what you get for this. Seriously, hit pause. I'm getting ready to tell you the answer. All right, here we go. Since the period of the pendulum is equal to 2 pi square root of L over G, we have to look at our variables here. Notice that they changed the mass on the pendulum, but we just said, hey, mass doesn't affect the period, and if I look at the equation, there's no mass in there, so that doesn't matter. So what about if I cut the length by 1/4? 2 pi doesn't really change. I get square root of 1/4, and G really hasn't changed either, and the square root of 1/4 is, in fact, 1/2. So my period should be cut in half. The correct answer is A. Congratulations. Okay, so when we looked at SHM, simple harmonic motion, before, we looked at its sinusoidal nature of both position, velocity, and acceleration over time. You can imagine if I have a mass on a spring that is oscillating under simple harmonic motion, and I roll a piece of paper behind it with a pin attached. What I'm going to get is this sinusoidal curve. So let's review those curves for a second here. So here would be a graph of, let's say, the position of an object over time that is undergoing simple harmonic motion. While we're here, why don't we review a little bit on the timing of all this. We will call one complete oscillation, we'll call that t, right? This is going to be t over 2, and so on. Okay. I'm going to make a graph now. I'm going to add the velocity graph for this same object. And by the way, you might want to consider where this object started. When t equals 0, notice that the object was at equilibrium. We were not at either extreme or either amplitude. So I'm going to go ahead and draw the velocity time graph for this. You might want to pause it, try that in your notes before you see what it looks like. So this green line is the velocity of the object. Notice that with simple harmonic motion, when the object is at equilibrium, its velocity will be at a maximum. And when its position is at its maximum, the velocity will be 0. And if you think about a pendulum, that makes some sense. You might also remember that the velocity of an object is equal to the slope of its position versus time, or the derivative of position versus time. So this green line is a graph of the slope of the blue line. We're going to do acceleration here, and remember, acceleration will be the slope of the VT graph. So this red line will be the acceleration of the object undergoing simple harmonic motion. Notice that the red line is the slope of the green line, or the slope of velocity, or the derivative of velocity. Another thing that's kind of interesting to notice, and this is our defining property of simple harmonic motion, is that notice that the acceleration and the position are opposite. That's what we said. Remember that acceleration is equal to negative omega squared x. There's our defining equation for simple harmonic motion. The acceleration is proportional to the displacement and opposite, which is exactly what you see on this graph. So the graph was a kind of a qualitative description of what's going on with simple harmonic motion. Now we're going to look at some mathematical solutions to that situation. So there's our defining equation for simple harmonic motion. Using some calculus, you'll end up with two different equations, this one and this one. Both of these are in your data booklet. Now, the first equation, this one here, what it's doing for us is it's allowing us to calculate the position of an object that's in simple harmonic motion at some time t later. Notice it has a function of t here. The second equation allows us to calculate the velocity of an object at some time t later. Now, it gets a little confusing here because you got sine and cosine in both equations, but we're gonna clean it up a little bit and make it a little bit easier. And the way we're going to clean it up is by using these things called boundary conditions. There's certain situations where these equations simplify. The first one is if at t equals 0, when we started our stopwatch, when we started observing this thing, and our t equals 0 point is when the object is at maximum displacement. X naught or x sub 0 means maximum displacement or amplitude. So if the object is at its maximum displacement when we started our stopwatch, then you end up with these two equations, where the position is a cosine function and the velocity is a sine function. It turns out if we started our stopwatch when the object is at its maximum displacement, this goes away and this goes away, and here are our equations, okay? We'll look at that graphically and see why that is in just a second as well. Now, the second boundary condition is if at t equals 0, if the object was at equilibrium. Rather than being at an extreme, if it was at equilibrium, then what happens is our equations look like this. Position is a sine function, and velocity is a cosine function. So if at t equals 0, we started with the object at equilibrium, these two pieces of the equations disappear, and this becomes our equation for position and for velocity of the object at some time t later. Now, what we can do is we can look at the graph we just did, the visual representation of the motion, to see why this kind of works out. So let's take a look at that. Okay, so let's look at just these two graphs of position and velocity. Notice this is starting off at t equals 0, we're saying that the object is at equilibrium, and the position function looks like a sine curve, and the velocity looks like a cosine curve. So when we're at let's see, where are we? If we're at equilibrium when we start, then the position is a sine curve, and the velocity is a cosine curve. How about that? Okay. However, if the object, instead of being at equilibrium when we started, what if it was at maximum displacement, or at its amplitude when we start? Well, that means t equals 0 would be right there. Okay, now we have t equals 0. And now notice that the position graph, this one, is a cosine curve. And the velocity graph is a negative sine curve. Let's see if that works out with the equations. So here we are. If at t equals 0, we're at maximum displacement, then the position is a cosine graph, and the velocity is a negative sine graph. So that's kind of one way of looking at how these equations come to be. So in summary, here's what you get. This is not in your data booklet, but you have those combined equations in your data booklet. If at t equals 0, and the object is at maximum displacement, then the position at some later time, you can calculate the position at some later time by using the amplitude times the cosine of omega times t. And you can do the same thing, find its velocity at a later time, negative maximum velocity times sine times omega t. However, if at t equals 0, it's at equilibrium, you're going to use these equations instead. You have another equation also in your data booklet that allows you to calculate the velocity of an object in simple harmonic motion at any position. Rather than looking at time, this is relative to some position. Okay? And the cool thing here is you can find maximum velocity using this equation, because you know the maximum velocity happens when its position is at equilibrium. We say 0 displacement. So this becomes 0 when we're looking for maximum velocity, and then this whole equation simplifies to that. So that allows us to calculate the maximum velocity of an object undergoing simple harmonic motion. All right, so here's a practice problem. Actually, 1, 2, 3, 4, 5 practice problems. Why don't you hit pause, get out a piece of paper and a pencil in your data booklet, try these questions out. We'll go through them here in just 5 seconds. 3, 1. All right, now we'll review them. If you haven't hit pause, shame on you. Okay, the period of oscillation. Well, since this is a position versus time graph, we can get the period of oscillation straight from the graph. 1 complete oscillation there, shoom, period, 2 seconds, done. 2 seconds, no problem. Okay, the amplitude of oscillations. Well, since this is a position versus time graph, then we can get the amplitude from the graph. Sure enough, 8, but don't be fooled and say 8 meters. Make sure to look at your units. Yes, we have 8 centimeters. 8 centimeters there, 2 seconds there. So to find maximum speed, we're going to have to use the equation we just talked about. Not that one. Let's go with maximum speed is equal to omega times displacement. And in order to get omega, you got to remember that omega is 2 pi over t times the maximum displacement. It'll give us maximum velocity. We just found t earlier. Pi is a constant. That should be easy. When you do that math, you should get something like 25 centimeters per second. 25 centimeters per second. Okay, so to find the speed at t equals 1.3 seconds, we're going to use the velocity equation that corresponds to the object being at maximum displacement at t equals 0. So that is going to be this velocity equation, negative omega times the amplitude times the sine of omega t. Okay? And for t, we will use 1.3 seconds. Omega we'll have to calculate. When you do that, you should get a velocity of 20 centimeters per second. And then the maximum acceleration. We'll use the defining equation for simple harmonic motion. And to find the maximum acceleration, we will have to remember that that happens when the object is at maximum displacement. All right? When we solve for that, we will end up with 79 meters per second squared. 79 meters per second squared. All right. Hopefully you're able to do those. Let me know if you have questions. So So the last equations we have to deal with in the simple harmonic motion unit are for the energy of an object undergoing simple harmonic motion. And we're going to be talking about potential and kinetic energy. And notice that those two values will be oscillating back and forth, the potential energy becoming kinetic, the kinetic energy becoming potential, back and forth, back and forth, back and forth. The kinetic energy is calculated this way, 1/2, remember with a particle that's just moving, its kinetic energy is 1/2 mv squared. So this is very similar. 1/2 m omega squared, that's just angular velocity, right, times the amplitude squared minus its displacement. That allows you to calculate the kinetic energy at any given location, wherever the object is located. And so you can find maximum kinetic energy this way. Since the maximum kinetic energy happens when displacement is 0, when it's at equilibrium, this can go away when we're looking for maximum kinetic energy, and we end up with that equation. So the total energy is going to be equal to that 1/2 m omega squared amplitude squared. Since the maximum kinetic energy is equal to the maximum potential energy, which is also equal to the total energy, that allows us to calculate the energy of a system. Those two equations are in your data booklet. Not, let me double check. Yeah, not this one. This one is not in your data booklet, but the first and the third are. Let's take a look at graphs of energy versus displacement and energy versus time in simple harmonic motion as well, and then we'll do some practice problems. So before I draw this graph, why don't you hit pause and try it in your notes here. What would a graph of energy versus displacement look like? And it's going to be two different lines. You're going to have one line for potential energy and one line for kinetic energy. So here's our line for kinetic energy of an object undergoing simple harmonic motion. Notice that the kinetic energy is a maximum when it's at 0 displacement, when it's at equilibrium. And notice that the kinetic energy is 0 when it's at either extreme, either amplitude. If I was to add potential energy, it'd look very similar, but opposite. So there's my potential energy. Notice I have 0 potential energy at equilibrium, maximum potential energy at either extreme. How about total energy? What's total energy going to look like in this situation? Well, it should be a horizontal line. Technically, that should be touching it, because whenever you have nothing but potential or nothing but kinetic, that's the total energy of the system, and it should stay constant, assuming no energy is being lost to friction. Another graph that we can look at is the energy versus time rather than position. And so this would be the kinetic energy versus time. Notice that we started off at when t equals 0, that it had maximum kinetic energy, so that's going to be at equilibrium. The potential energy should basically be in kind of an inverse of this. So there's my potential energy with time. Notice that's the opposite of kinetic. When kinetic is increasing, potential is decreasing, and vice versa. When I have no kinetic, I have all potential. When I have no potential, I have all kinetic. The other thing you might notice is that these energies are always positive. There's no negative energy. Energy is a scalar quantity, not a vector quantity. So it's always a positive quantity. That's not actually technically always true, but we'll go with that for now. The last thing that I would add on this would be the total energy. Very similar to last time. It would just be a horizontal line. There's my total energy. Does not change, assuming no losses to friction. Okay, here's an IB problem for you to practice. Hit pause, time yourself, give yourself 90 seconds. See what you can do with this. This one's a little bit tricky, though. I'll give you that. Are you done? You got it? Did you hit pause? So here's our equation for total energy. 1/2 m omega squared x naught squared. You might quickly say, oh, well, we tripled the mass, and we doubled the amplitude. I have to square that, so that's going to be 4 times 3 should give me 12. That would be a quick answer. Unfortunately, that's not the correct answer, because the other thing to remember is that omega is equal to 2 pi over t. And the period of a mass spring system is affected by the mass. Remember that in a mass spring system, the period is equal to 2 pi m over k. So what I can do is I can take all of this and plug it in for t there, and watch what happens. I end up with that, and when I simplify, 2 pi cancels out, and omega is equal to the square root of k over m. So omega squared is equal to k over m. Now I will take this, throw that up there for omega squared, and I'll end up getting that. Total energy is 1/2 m k over m x naught squared. The m's cancel out, become irrelevant. So the only thing that affects it in this scenario is the amplitude. The amplitude was doubled, but I square that for an answer of 4. 4 times the energy. B is the correct answer. Okay, that last one was a bit challenging. Let's try this one out and see what you can do. This one's also a bit challenging, but remember, these are higher level questions, so this is harder stuff than the standard level. So hit pause, work this one through, see what you can get. No, really, hit pause. Come on, I mean it. Okay, I'm getting ready to show you the answer here, so if you haven't hit pause, shame, shame, shame. So the equation is asking for the potential energy of the system. I mean, the problem is, but we don't have an equation for potential energy. We only have an equation for kinetic energy. So let's work with that, since we know that they will be kind of inverse of one another. So here's our equation for kinetic energy when the object is located at a certain position x. I'm going to rearrange this just a little bit. Okay, so I've rearranged this just a little bit to figure out the kinetic energy when it's located somewhere. I'm going to call this, well, let's see. It says when it's 0.2 times the amplitude from its maximum displacement. So that's the same thing as saying it has a displacement of 0.8 times its amplitude, right? It's 0.2 from the maximum. That means it's 0.8 from equilibrium. So I'm going to call this 0.8. And then I'm going to square it to get 0.64. Okay? And so then basically I'm going to call this everything over here basically 1. Right, because that would be like its maximum displacement. So that means, since I'm subtracting these, my kinetic energy is 0.36, or 36% at that location. But they didn't ask about kinetic energy. They asked about potential energy. So if it's 36% kinetic, that means it's going to be, dun, 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 64% potential. And that's the correct answer. The potential energy is 64% of the kinetic energy. Man, these are kind of tricky, aren't they? Okay, so let's just go back to where we started and see how we're doing. Make sure you understand the equation for simple harmonic motion. A equals negative omega squared x. That's a good understanding to have. And energy changes in simple harmonic motion. Can you solve problems of all these things with all those equations? Can you look at the different interchanges of energy, and can you solve problems involving energy? Okay, and the pendulum and the mass spring system are important components of this unit. There's all our equations. I'm pretty sure we covered them all. Make sure to review them and practice them, and good luck. Let me know if you have any questions.